the difference between potential energy and the potential field. The potential field is the cause of potential energy. Therefore, they can't be the same. Although the definition is the amount of work per unit charge, it does not give it justice with that definition. There's a much deeper meaning, and that's what we want to get at. So the overall is that potential energy is stored work, and this involves the interaction of two objects. The potential field is about imaginary work. That can be done and only involves one object. So I want to expand on that picture right there. So let's paint a picture of these scenarios. So the first one that I want to look at is that I'm going to imagine that my hand is going to be pushing on a block. So Carlos's hand is pushing on a block. So if I have a block, then we could imagine something like this here. I have a block on a surface, and my job here is to actually move it from here to there. So what I'm doing here is that I'm applying a force with my hand on the object, and then I'm going to move this thing a certain distance. So then I'm going to move a distance, let's say that amount right there. So what you're seeing here is that work requires two things. Carlos's hand, that's going to be the source of the work and the block, which is going to be the object that work is being done on. So we require two things. Now, the question that I have now goes like this. What do you call Carlos's hand before he pushes the block? What would you call it? In physics, we say it's the potential to do work. One imagines the work that can be done, which is not actual work. It's imaginary. This only involves one thing, the hand. Now I can repeat this with another really familiar thing, and this is a battery and a light bulb. So once again, work requires two things. In this case, we have a battery, and the battery is the source. And what does it do? It pushes charges. It does work on charges, and then this guy's going to be the object. I mean, we can also say that the charges and the light bulb might be on the same thing, but it's really the charges here. So what do we know? The battery does electrical work to move charges that light up the bulb. So that's two things, right? So now if I have a battery, so if I'm looking at this battery, you could imagine here that we have a standard battery. It's going to look something like this. And what you're going to find here is that the top here, that's the positive end. And the bottom here is the negative end. So now I have a light bulb. And so the way I connect it here is that I typically connect, let's say, a red wire to the side of the case, and then the black wire comes from the negative and it comes right to the bottom. So if you connect this, you're now pushing charges along the wire, and then the bulb lights up. Following the same process as before, question: what do you call the battery before it's connected to the light bulb? We call it the potential to do work. It's not doing any work because it's not connected. Again, one imagines the work that can be done, which is not actual work. This, again, involves just one object, the battery. And believe it or not, it's the battery that's the potential field. The units of electric potential field are voltage. And a lot of times we don't say the word voltage, we actually just say volt for short. So the units of electric potential field are voltage, while potential energy units are joules. Different units immediately imply that they are two different entities. They have different units. Once again, the potential field is the source of the potential energy function. So in the language of electrostatics, the electric potential field is typically defined at the undergraduate level as V of R. And we typically don't say electric potential field, we just use the word potential. And I would say this is the most common. But there's another language that they call it a node voltage. Here, this is the language of circuits. But this is what we have. So now our job is to start to look at what are the connections here. Let's now give a proper introduction to the potential field. People stop thinking about the word potential field, but it is a field, just like the electric field. It has a value at every point. The potential field is a scalar, whereas the electric field is a vector field. There is a connection between the electric force and electric field. A similar connection occurs between potential and potential energy. So just for the sake of making things clear, define charges little q as the test charge, and then big Q as the source charge. So now let's look at these connections here. So when I look at the connection between the electric force versus the electric field connection, what do we see here? Well, the electric force looks like this. And the way we connect it to the electric field is that we isolate the source, all the details about the source. So in this case, we say that the electric field then is a ratio of the electric force per unit charge. Well, if we put this all together, then you're going to see here is that that little q is going to cancel out because we have this divided by little q, which then gives us 4 pi epsilon r squared divided by q. So this guy right here contains everything about the source. In a very analogous way, we could say the same thing about potential energy versus the voltage or the potential connection. So our potential energy we've written as 4 pi epsilon r little q minus 0. So now, in a very analogous way, we isolate the source details. And when I do that, we then say that the change in voltage here, or the change in potential, is then the change in the potential energy divided by little q. So it's the energy or the work done per unit charge, as they say. So then it's the same type of thing. We have Q, big Q, and then we have almost the identical expression, which will be 4 pi epsilon r squared divided by little q. And just as we saw above, these q's cancel out, and then it leaves us, by the way, I put a square here, which was not correct. So then that leaves us with 4 pi epsilon r into q minus 0. Once again, it contains everything about the source. So by writing it this way, the definition of the potential field is that this guy is the change in the electrical potential energy divided by Q. Now, in general, this is not a useful relationship. This is really just for to show the connection. So let's do a couple of remarks. The electric potential field is a scalar field. Not a vector field. This can be quite the change in thinking. Since vector fields follow superposition. Over the last three chapters, we've focused on superposition, but scalar fields do not follow superposition. At first, it's likely that you're going to struggle with this because it's a change, and you're going to have to learn that change here. So then what we want to look at here is that if I look at the units of measurement, even though we've already stated them, let's make them nice and clean definition. A unit of potential is a unit of potential energy and a unit of charge. So this becomes now a joule per coulomb, and this is what's defined as 1 volt, which is typically written as V. And then the last comment is that the work energy theorem defines mathematically the potential field. And it goes like this. We define work. The work of the electric field is then going to be this guy. But the electric force, we can write that in terms of the electric field here. So that work done by the electric field is always negative of the potential energy function. But we've already defined the potential energy as minus Q times delta V of R. And where I get that from is from this relationship right here. So now if I rearrange terms here, you're going to see that we're going to get that delta V of R is V of R minus V of R reference, which is then the negative integral of the electric field dotted with the displacement vector. This is our definition of the potential function mathematically. Once again, always envision imaginary work being done to interpret the potential field.